Alrighty, so last time we started the communication protocols section of the embedded system course, and the first protocol that we seen together was a serial one, and it was called UART. So UART, sometimes also known as USART, is a serial communication protocol that is present there in many of the microcontrollers out there. And when you see USART instead of UART, this means that the protocol or the module is enabled to be used as a synchronous for synchronous communication as well as for asynchronous ones. And the thing that I told everyone in my face-to-face lectures, naturally, is that seldom are the people who use USART in its synchronous version. Most of the people, they use it for the asynchronous version of it. Right, and we've seen in the datasheet of the Atmega 328P. So this is the one that is present on the Arduino Uno board, for instance. We've seen that we only have one module, USART module here, and it's connected in that particular microcontroller to port D. Hence, you can use one of the some pins from port D to be able to communicate serially using the UART protocol to other modules or peripherals or microcontrollers. Alright, so in today's lecture we're gonna see how to program the serial interface, which is also known as the UART or the USART. It depends on the module that is present in your microcontroller. Well, we're concerned with the USART component that is there, and we're gonna see how to program it in order to be able to communicate between two different entities. All right, so what we're gonna do first, as usual, is check out what has been done, what has already been done. And we see in some library in the Arduino platform is called a serial, right? And we can see that this is the object, so the serial object that is concerned with the UART or the USART. Fair enough. So if you're having an Arduino Uno board, for instance, you know that you only have two pins concerned with the UART, one for the RX naturally and one for the transmitter. So one transmitter, one one RX and RTX. However, in other boards such as the Arduino Mega, you can see that we have more than a couple of pins here. This means that we have more than hardware modules that are UART modules or USART. Fair enough. Alright, so as I told you earlier, most of the people, they do not use UART or USART in a synchronous manner. So basically, synchronous is not directly supported by the Arduino firmware, so you cannot see it in the high-level libraries that we have here. However, this doesn't mean that you cannot use it in a synchronous way, and to do so, all you have to do is get down to the registers level and put the right combination of ones and zeros in order to have the option or to enable whatever the synchronous or whatever functionality that you want to use with this particular module. Alrighty, so what I need you to understand here is serial is the object, so you can see it as an object from a Java point of view, from object-oriented or OO point of view. And then we're going to see a bunch of functions that are related to that particular object. Fair enough. So in this case, we can only have one object because we only have one serial module. However, in that board, for instance, we can have multiple objects. All right, so serial 1, serial 2, serial 3. So you can see it as a new object from the class that is serial. You can look at it that way. Alright, so serial begin. As I taught you before, when it comes to the UART communication protocol, we need to coordinate a couple of, some things needs to be coordinated between the sender and the receiver prior to the establishment of the communication itself. So prior to the transmitting of the bits. So what are those? Alright, so yep. So we need to specify the speed, and we've given it a very beautiful name. And then we needed to specify a couple of things such as the length of the data, whether we're gonna use the parity bits, and if so, whether it's going to be an even or an odd one, and the number of bits to deal with the stop bit, stop field. Alright, so let's check this out. So we have a function that is called begin, that is, of course, you can see it as a method of the object serial here, and we need to specify the speed, also known as baud rate, right? And we said we're gonna use baud rate. And the config is everything related to the size of data, whether we're using the parity bit, and the number of stop bits, for instance. And this particular function exists in a different format. So here we have two parameters. We can have the version of it where we only have one parameter, and this is what is commonly used, by the way. And all we have to do here is to specify the baud rate. All right, this means what? If we're doing that manually here, this means that something is going on in here. What is it? This means that we have some kind of default value for the config here. All right, so the configuration, the config could be anything like 5 bits to represent the data without using the parity bit and using only one a stop bit, or I don't know, 8 bits to represent the data with the odd parity bits and one what do we call it, one stop bit, or 2 stop bits here, for instance. All right, and here, can anyone guess what is the default value? Well, it's in red. So basically, if I don't specify it using the config, well, the default value for the config would be serial. It will be 8 and 1, meaning that I'm having 8 bits of data. I'm not using the parity bit, and the last thing that I'm doing here is I'm specifying only 1 bit to mark the stop. Alrighty. Now, serial begin, this is where we coordinate, and then serial write. Naturally, you can trust your engineering guts here, and they're telling you that this is where what I use to send data. Alright, so here we can write a byte or a series of bytes to the serial port. Alright, so we're gonna see 3 different versions of that particular function. So first off, if we use it with the parameter that directly takes a value here, so this means that I'm only sending 1 byte, a single byte, and this byte represents whatever decimal value that I'll be having here. Alright, so yeah, if I use the second version of it, and instead of a value here, I'll be having a string, right? So a bunch of characters. So this means that I'll be sending a series of bytes, right? So if my string is only 1 character, that would be 1 byte, but naturally my string should have more than 1 character because it's a string. And the third and final version that I'm seeing here is more flexibility for us engineers. So basically we can specify somewhere a buffer and point to that buffer here, and then specify the number of bytes that I want to send from the buffer. Fair enough? So let's see an example here. So first thing I need to do is set the baud rate, right, using the begin, and then inside my perpetual loop, well, I'm sending the whatever byte represents the value, representing the value 45, right? So the byte, the 8 bits, well, are encoded to represent the value 45 here. And what about that one? Can anyone find out the number of bytes that are being sent here? So this is the string version of it, and we can see that it has 1, 2, 3, 4, 5 characters. So each character is naturally 1 byte long. So this means that I'm sending 5 bytes. So 40 bits of data here. 40 bits that I'm sending. And if ever needed, it will return the number of bytes that are being sent, so I can use them somewhere for some reason or another. right, so let's see here. Imagine that someone is giving you that. Yeah, I mean, you just discovered the computer where some stuff are being sent, maybe some espionage or something like that going on. So you can feel that, yeah, someone is trying to send serially. So using the UART module here, sending the baud rate, and then we're sending 5 characters, so a string saying hello, and then a bunch of things. Well, if we're gonna go ahead and play bonds and try to decipher what this means, so let's think for a second. What would that be? So I'm sending a bunch of values, so what would that be? So here 10, 17, 71, 85, 67, and 10 again. Alright, so alright, so probably it is some ASCII code. Oh yeah, let's see. Maybe it is. So here 10 is a line feed, so I'm back to the line, and then I'm sending 71. So 71 is a G, and then 85 is a U, and 67, so 67 is a C. Okay, so makes sense. And then a line feed again. So naturally, on my serial monitor, I'm seeing whatever been sent from my Arduino board. Alright, so if I'm sending, I could also be reading or receiving. So in order to receive, we're going to use the read function here. So let's see an example. It will be easier. So I'm defining some kind of variable that I might be used later, right? I have my setup function, and then I need to coordinate the baud rate and use the default value of the other config. Alright, so in my loop, what am I doing? I'm doing something here, and that something is the available function. Means that I'm gonna check if I have in my buffer some data that is there. Alright, and this particular condition here, I'm checking if I have at least 1 byte of data that is in my buffer. Alright, and then if there's something there, I need to read it. So all I have to do is use the read function and store it in the variable that I defined here. So I'm reading the incoming byte, so 1 byte at a time, and then I could be, sending it and to print it out somewhere else using the serial. All right. By the way, can I connect my serial? Let me see this one. So imagine that this is my microcontroller. I have my RX and my TX. All right. So I need to connect them to the entities that I'm communicating with. So my question is, can I connect that one to some entity and that one to some different entity? So as engineers, we always answer yes, right? Because I could be getting some data from some entity that are transmitting to me, and sending some data to another entity to display it somewhere or something like that. I mean, why would we do that? There are some other things that we might use, but it doesn't mean that it's not feasible. There's always a way. All right, so when there's the will, there's a way. Oh, okay. So the question that I'll be asking here is the size of the serial buffer. So it's 64 bytes, so you need to think about it. Well, it doesn't matter. I don't really care about the value per se, but I care about if it's too big or too little, there be cons and pros. But because we're in the RTS domain, right, so real time, so it makes sense to have somewhere in between. So I have enough space to get the real-time data and get to deal with it, right, and not lose some data that is coming here. And I don't want to take a lot of time to process old data because it doesn't make any sense, because my data needs to be in real time. Alrighty, so I have a flickering thing here. Interesting. Let's see an example. I want to see a function that is called serial event. Right, so I don't want you to read the comment here for now. We'll see it later. Let me try and do that. I don't know if it's still readable, but I don't care about that. Alright, so this is not my code. This is what you might find in the documentation of this particular function as an example. So let's see here. What am I doing here? Let me use the laser pointer. It will be easier. Alright, so I'm trying to create some string that I'm calling an input string. So most probably this is what I'm gonna use in order to, as a container to put my input data. And I'm using a bool here, so most probably I use bools, booleans, in order to do some testing, some conditions. So this can be seen as a flag, string complete, and I'm initializing it to false. Then I have my classical setup function where I'm I'm fixing the baud rate. Alright, and then this is, you're not familiar with that, but that doesn't really matter. This means that I'm making sure that there's enough memory for 200 bytes here. Doesn't really matter. And then I have my perpetual loop. So in my perpetual loop, I'm testing the flag and I'm doing some stuff. So let me see. The very first execution, my flag is at false, so I'm not getting into that condition, so I'm not executing anything here. The only way I'm executing whatever I'm doing here, so maybe to print the incoming string and do some stuff, right, is if the string complete becomes true. And who might do that? So maybe this function. So let's check this out. So in my serial event function here, I'm having while serial available. So while there's something to be read in the buffer, I'm gonna read the bytes. So here it's casting, so a character is normally 8 bits, right? So I'm getting the 8, whatever I'm reading here, I'm making sure that it fits the character here, and what I'm usually reading here is 8 bits, so 1 byte. Alright, and this is concatenation. I believe you've seen that with your Java instructors. I hope so. So I'm pushing whatever I'm getting here into my string, right? And when I reach the end of the line, so a new line character here, I'm gonna finally raise my flag to true. This means that the next time that I'm in my loop, I'll be able to get in here and print out the string that I got, right? The first string that I got, and then empty it, and then set back my flag to false. So here I keep on reading, until I read everything that I need, and I need to do that if I've reached the end of the line. Alright, so my big question is, does this feel like more like interrupt based mechanism or something else? So you need to remind me of the two ways in order to detect events, and we talked about that earlier. So one of them is interrupts, that's for sure. So I will ask a question, and whenever the answer is there, someone will tell me, okay, so your answer is ready, so stop whatever you're doing, deal with it, and then go back to whatever you were doing. Or I can do it in another way. What is the other way, and what do we call it? So the other way is to keep on asking the question, is it there yet, is it there yet, is it there yet? And this is what we call polling. Alright, so polling and interrupts. So does this feel like polling or interrupts? Although it feels like I'm spending my time here, and when something is coming here, I'm back to here. This is polling and not interrupt based. And to cut it short for you, interrupt based is not supported by the people from Arduino. This doesn't mean that you cannot. This doesn't mean that you cannot do it. This means that it's not there, so you need to create it from scratch, and it's not that hard. Well, relatively. Right, so let me erase that. So alright, if we read the comment here, so a serial event occurs whenever a new data comes in the hardware serial RX. This routine is run between each time loop runs. So each time my loop is running, I will go there, check it, alright, and then go back to my loop. So this is why they're telling you if you're using any delay inside the loop, that will delay the response to whatever incoming data that you're having here. Alright, so this feels like I'm executing my loop, I'm going there, I'm executing my loop, I'm going there. It's not like I'm interrupting my loop and to go there. Fair enough? Alright, so this has a more polling feeling than an interrupt one. So hold on, so if I cannot do interrupts in like proper interrupts in high level Arduino, I would be able to do it in a different way. So yeah, back to embedded C and back to programming registers. I'm only going to give you a hint of them, and that's it, like, you know, a little taste of them. So let's check this out. So here I have my main function. Give me the pointer, please. So here my main function, forgot about that for instance, and here it feels like I'm doing something to something that looks like a register. So names, register names. So let me try to decipher it, even though I didn't. I'm not going to open and read the data sheet right now. So RX, this sounds like, you know, receiving, right? C, I don't really care. And IE, so what would that be? IE, so I would be interrupts, and E for enable. So this feels like bit masking and the stuff that we done a lot. So this feels like I'm setting this particular fields in the register. Fair enough? So this means that I'm enabling the interrupts of upon reception. Fair enough? I can do a lot of stuff in my main loop, you know, perpetual thing, and I don't really care about that right now. So the question is, if now I'm inside of my while here and something is being received, right? So what would happen? So an interrupt will happen. This means that I will halt whatever I'm doing here, go to the ISR, so to the interrupt service routine or the interrupt handler, right? And this is here. So this is the vector. Remember when I talked about interrupts earlier? I don't know in which lecture, but you know, it was before the communication protocols, yeah. And we've seen that we have different priorities for the vectors. So for the interrupts, and the highest priority one is which interrupt? The reset, correct. All right, so here we know that this is the ISR that should be dealing with the USART reception. So the receive something, stop, come here, and I'm doing something. So apparently I'm reading maybe some data, the data received, putting it somewhere to be able, you know, in a variable, to be able to use it later on and, you know, act on it. Doesn't really matter. All right, so this is what happens. Awesome. However, remember when we deal with USART or UART, we need to coordinate some stuff prior to everything, you know, that we've seen happening here. So this is the role of that particular function, and I'm going to show it to you just a little bit. So here you can see that this function, right, is called first. This means that and it's in the name, you can guess it, you know, from the value. I mean, we don't care about the values, but it seems like we're trying to fix the baud rate here, right, in a way or another, and we can see the registers that are concerned with that. And then we can see that we're using the asynchronous mode of it, whether or not we're using the priority mode, the priority bit, the number of bits for the stop bit, and how many bits for the data. So you can see that they are somewhere where I'm not seeing that. Here we have some values and we're trying to program them. So this is the easy part, and let's try and guess what is that here. So what does it feel like here? So this feels like setting up a particular field in my register here. So this one is concerned with RX and TX, and EN feels like it's enabling, right? So it feels like I'm enabling both receiving and transmitting. Fair enough? So I'm going full toplex. Awesome. And the last thing that I need you to notice here is the red thing here. What would that be? So that would be the function call to enable global interrupts, and this is needed to make sure that interrupts are happening in my system. Alright, so that was the last or the end of the UART protocol, and now we're gonna tackle the very first communication protocol that I've personally used as a student. That was the equivalent of the bachelor project, if I may say so. Back in the days, definitely. And it's called I2C, and we've talked about it real quick somewhere in this course, and there's another name for it. Do you remember what that is? It's the two-wire interface. Anyways, we're gonna see it right now. So this is another serial protocol that we're seeing, and I've personally used it on the project. The first project that I worked on as an engineering student was a robot, a mobile robot, and that was a huge deal back then. I'm talking about a long time ago. All right, so a serial protocol, however, this time it's a synchronous one. All right, so if I ask you, a synchronous serial protocol means hardware-wise, how many wires will I be needing minimum? Right, so let's think about it for a second. So serial one, we said that data is broken down to a stream of bits, so basically I might need at least one wire for the data. And because it's a synchronous one, unlike an asynchronous one, I need something to have the clock pulses, so I need another wire. So at least I need two wires to have a synchronous serial protocol. Alrighty, and this is the case here. Alright, so it's also known as the two-wire interface, and back in the days, even earlier than my days, that was created to connect low-speed peripherals for short distances. It was created by Philips, right? But now, so that was an in-house protocol that they used to use, but now it's almost everywhere. In every microcontroller, you would see a I2C interface. Right, so it's a new notion here. So a multi-master, multi-slave, and you had some kind of info about master-slave, paradigm in my OS course last year. So you remember when we talked about distributed OS? So we had one entity having the kernel or the major components of an OS, and then distributing the different other components and tasks over different processors, for instance. And here the challenging part would be, so it's easy to have a master slave, one master with multiple slaves, right? However, the problem here might be with the multi-master. This means that I have more than one master trying to act at a time. So we'll see how to tackle that and what is exactly meant by that. And here we can see a schematic showing the bus. So anyone can see that we're having one master here and three slaves, and my slaves are in ADC, DAC, and something else. And the master is of what nature? So both the master and one of the slaves are microcontrollers. All right. And as I talked about it here we can see two different wires, right? And of course I need some kind of voltage because I'm dealing with electricity after all, right? So the two wires here, and they are named SDA and SCL. So you can feel it that the SCL is the clock wire and the SDA is the data wire. All right. So a couple of keywords we're gonna use later on, so I need to make sure that you understand it. However, because you're not in front of me, so you cannot give me any feedback. So a transmitter is the device that sends data, whether it's the master or the slave. All right, so transmitter sends data. Receiver, it is the device that gets data, receives data. Fair enough? Doesn't matter if it's a master or a slave. Master now. It is the device that initiates the transfer, generates the clock on the clock wire, and ends a transfer as well. Fair enough? So this is its role. The slave, it is the device, the passive, should I say, device that gets orders from the master, right? So it is addressed by the master. The multi-master paradigm means that more than one master, right, is trying to attempt to control the bus at the same time, and we'll see how to deal with that. So this means what? A couple of things, should directly come to your mind for that issue. So we need to deal with two different things. What are those? Can you try and imagine them? One of them is to make sure that there's no corruption when it comes to sending the data, right? So basically, if two masters, for instance, are trying to control the bus, and one master is trying to get data from some slave, and another master is trying to, send data to some other slave. So because we're sharing the same line, so there will be some corruption, that's for sure. So we need some kind of arbitration mechanism here, all right, to make sure that only one master is active at a time, or acting, not active, acting master at a time. That's a better way to describe it. And what is the other thing? So if this happens on the data wire, we need to make sure that some kind of synchronization is happening on the clock wire. Alright, so we need to make sure that all the masters, because only a master can generate the clock signal, are synchronized with each other. And we're going to find out how later on, don't worry about that. Alright, so let's see an example here. So what you're looking at here is, let's see, it looks like in I2C bus, right? So SDA, SEL, that's classical now. I'm seeing how many entities, 1, 2, 3, 4, 5, 6 entities. How many potential masters are we? So how many possible masters are we seeing in this particular schematic here? So let's try and engage our engineering feelings or guts. Alright, so this is a microcontroller. Most probably it would be a master, probably. This is an LCD. So I cannot imagine where an LCD could be a master. It doesn't make any sense. An ADC, never a master, that's for sure. A memory, never a master. Oh, alright, awesome. Another microcontroller. So this could be another master. So this is a potential master, and this is a potential master. What about that one? So it's an FPGA, right? So it's a gate array here. So this means that I can program, I can wire it to be a processor or a microcontroller or something like that. So this is the third potential master here, right? So let's see a couple of examples here. So let's imagine that this is my master, and it needs to send some information to the B slave. Remember, everyone is sharing the same bus, so I need a way to make sure that I'm addressing this one. Alright, so I need to specify the address of that slave, so microcontroller B in that case, then send the data, and then remember, what is the last mission of the master is to terminate the transfer. So transfer is done, maybe someone else can do something else, or I can personally as a master do something else, or a different master, for instance. Alright, so let's see another example. Now I want it the other way around. I need my master A to receive some data from slave B. So let's see that. So who needs to initiate the transfer? It's always the master. Alright, so microcontroller A here will send the address, send something to the microcontroller asking for some data. Then, and only then, the microcontroller is able, the slave here, microcontroller B, is able to send the data to microcontroller A, which is the master. And once I received all the data that I need, I can terminate the transfer. Fair enough? Awesome. Alright, so let's talk a little bit about the wires here, and all I need you to understand from that is, so here you can see that I'm having some kind of voltage, that is almost 5 volts, roughly 5 volts with the delta, doesn't really matter. But what I'm trying to say here is when those lines are free, so no one transmitting anything, they're maintained as at a high level. All right, so bidirectional, of course, so because we can either send or receive, etc. All right, and when they are free, so no one is sending anything, no one is generating a clock, both of them are left at a high level, exactly as for the UART, by the way. However, the good thing about the I2C bus here is we have different speeds, and they can go up to 3.5 megabits, which is awesome. Alright. Alright, so a new thing here that is an important one. It's about data validity. Alright, so before putting the text, I'm gonna try and explain it. So I'm having my master, I have some generated clock signal here, right? So if I want my data to be valid on the SDA line, the data should never change whenever the clock is high. It is only allowed to change, we'll go to 1, from 1 to 0 or 0 to 1. It's only allowed to change when I have a low state here at the SCL line. Fair enough? So let's see the text. This is exactly what I said. So SDA line stable, either 1 or 0, doesn't really matter, during the high period of the clock, and the change can only happen whenever my clock is at the low. Alright? Each bit transferred, I need to have a pulse. So if I'm sending, let's say, only 4 bits, however, I need to send 8 bits. Anyways, doesn't really matter now. If I'm sending 4 bits, I will need 4 pulses here. We good? Here in this case, we're saying, let's see, more than 2, because there's a dot line here. Doesn't really matter. But here, for instance, we can see that this is considered to be 1 bit. Right? So when the clock is high, this means that this should be stable, and whatever stable value I have here, this means that it represents a data bit. Alrighty, so if the data should be stable whenever I'm having the clock here at high, how do I mark the start and the stop conditions? Because remember, whatever the protocol is, I need some way to coordinate the stop and the the beginning and the end of the transmission, or at least the transmission of one packet, but in this case the end of the whole transition. So let's see that. So remember, for the data to be valid, I need to be at no changes are allowed at a high level here at the clock. So to mark the start, for instance, when the clock is at high, all I need to do is take it from high to low. Because remember, when no one is using the lines, they're maintained as at a high state. So basically, to know that something is going to happen, a transmission is happening, all I need to do is bring down my data level here, data line from 1 to 0, while my SCL is left at 1. Then I can start generating and do the stop line, right? So what about the stop condition now? Well, it's the exact same thing, but in the opposite direction. All I need to do is have my SCL at high and pull up my SDA from 0 to 1. Alright? So this would mark a stop condition. Right? High to low, where SCL is high, and low to high, the other way around for a stop. Alright, so byte transfer. So this is what happens in this protocol. I2C, I'm sending 1 byte at a time. Check this out. So it's 8 bits. So I'm seeing here my start condition. Let me verify that. So my SCL is at high, and I'm bringing high to low the SDA. So this marks the start. Then I'm gonna send my bits. Right, so I'm sending 1 byte for now. So remember, for each bit I need to have a clock cycle to be maintained stable, to for the data to be valid. So here I'm having 8 bits, 1 byte to be sent, so I need 8 clock cycles. However, you can notice that I'm having a 9th clock cycle here. What would that be for? So this is for the ACK, for the receiver to say that if whether I've received correctly the byte or I didn't receive it. So if there's an acknowledgement, this means that the byte has been received correctly. If not, this means that the byte has not been received correctly and I need to do something about it or not. This is your choice. It doesn't really matter. Right, and here you can see the stop condition. So clock at high and I'm bringing from 0 to 1, so I'm good here. We good? So 8 bits of data need 8 cycles, an additional cycle for an acknowledgement from the slave, because it makes more sense that a slave is receiving data from the master and telling that if yes or no, I did receive it. Because if it were the master that is not receiving, well, it won't necessarily send an acknowledgement to a slave. All it has to do is restart the transmission and ask the slave to send the data again. Alright, so let's see. This is what I said. And the last thing that you need to do, but you need to know, but you can always check it, that we send in I2C the most significant bit first. Alright. So the schematic is kind of weird because naturally I would have put the MSB here followed by all the bits till I reach the ELSB. However, you can see that this is cycle number 1, 2, 3, 4, 5. So it's kind of weird. The schematic is weird. Anyway. Alright, so the ACK, we talked about it. So this is some text. Yeah, how do we mark it in ACK? Well, on the 9th pulse, right? Remember that? Let me get a pen here. So I have my 8 pulses and then I have an extra one for the ACK. So that would happen. Once I'm done with that, normally the line will be back to high state, because remember, if no one is doing nothing about it, so the default value of my line is a high level. So in the 9th cycle here on the clock line, sorry, right? All I have to do, all the slave receiver can do, have to do, is to bring it down. So on my 9th, I need to have a low. If I have a low, this means that someone is maintaining it at low, and this is to mark the ACK. Alright? So if for some reason on the 9th cycle here, I did not get to bring down my line, right? So it's left at 1, for instance. This means that I did not receive it. And this is what we call a NAC. So this is a NAC. Let's see it here. Laser pointer. Alright, so check this out. I'm having my 8 bits and I have my acknowledgement here. So I'm good. That's weird. Why am I not seeing a NAC? Oh yeah, right. So this is what happens. So here, if I'm done with my 8th and this line is back to 1 here, this means that on the 9th pulse, right, I did not bring it down, so it was maintained on 1, so there's a NAC. Right, SDA remains high during the 9th. I'm good. Yeah, but my challenging question is, let's try and imagine why wouldn't a slave receiver send a NAC? Send an acknowledgement, not a NAC. Right, so let's think about it. Remember context real-time embedded systems. What could that be? The easiest answer is if the slave is dealing with something in real time. So maybe an interrupt, something like that, if it's a microcontroller, let's say, right? The other thing would be, remember, I need to specify the address of the slave. So maybe the address that I'm trying to get to send data to is not connected. So there's no one with that phone number. Or maybe something went wrong with the data, so he did not understand it, right? And what else can you think of? So no receiver dealing with a real-time function, something went wrong. And the last thing is, ta-da, remember, I have some kind of buffer so I can get the data, incoming data. Maybe my buffer is full and I cannot take it anymore, right? Awesome. And that was the last slide that we tackled in the face-to-face lecture. And this is a real-life situation analysis that I'm, always giving examples of. So here, imagine that someone is hired you as a, I don't know, let's call it a task force, and you're trying to analyze this particular schematic. So first off, you can see that you recognize the names here and two lines. So basically this is the I2C protocol. You can feel it. So it's an I2C bus with a data line here and a clock line. And you can also see that there are 2 bytes being transit here. Alright, and we can see ACK and ACK and stuff like that. Alright, so let me see here. So I have my clock at 1 and I brought down SDA from 1 to 0, so this is exactly a start. Let me go and see if there's another stop here. So this one is at high. What? I'm bringing it from 1 to 0 again. What does this mean? It means that it's another start. Yeah, it makes sense. So it's another start. Maybe it's a restart. Good. So let's see. So this is my start condition, right? And I have a byte here, so 8 bits, and I have another byte here, so 1 to 8, so 8 bits is également, no, again, all right? And then I have a NAC here, so it's a good acknowledgement happening here, but I have a NAC here because you can notice that this one remains at 1 on the 9th pulse here. And the last thing is another start condition, and in this case, when I have no stop between the two starts, this is what we call a repeated start. So this is classical, we're good. So this one has been received, this one apparently not, and the master decided to restart the what do you call it, the transmission. This is not it. This is not my problem. Can you observe something weird about this particular schematic? So you can notice that if everything's fine here, so basically the clock cycles should look like each other indefinitely until I'm done. But there's something weird. Can you see where? It's here. Yeah, something confusing about that one, because remember that one has been received, so naturally I would start with the 1 of the second bit. So what happened here? This feels like it's bigger than it should be. Think about it. Pause the video and think about it. Take your time, because it's an important example of the things that you might see later on in your life, professionally, or in your life with me. Alright, so this feels like, although I acknowledged that I got your byte here, but maybe I'm about to lose it. Lose it in the sense of maybe I cannot handle any incoming bytes anymore later on. So this is a desperate attempt to stretch, to make the sender hold it for a second, right? So for me to deal to whatever I need to deal with in order to try and make it possible for the next byte to be received. But unfortunately that wasn't the case here, alright? And this is what we call clock stretching. You know, it's like someone is pulling on the clock to stretch it to buy some time. Fair enough? So yeah, So you can read it. So if a slave cannot receive or transmit another complete byte, right? So it can, and this is the only time that a slave is allowed to deal with the clock, because remember, it's the master's responsibility to deal with the clock. So you can stretch it out, and when it's normally ready, it will let it be, right? However, it's not a guarantee that everything will go as we've seen, and go as planned as we've seen in the earlier slide. And this is what we call clock stretching, and it's definitely optional. Alright, so this is the end of today's recording. Hope to see the people that I haven't seen this week. See you next week, right? For the face-to-face lecture. If not, well, we'll see you sometime, someday.